in previous class. So we learn Thevenin's theorem. Now go for Norton's theorem. Here, like Thevenin's theorem, Norton's theorem provides a method of reducing a more complex circuit to a simpler equivalent form. That is, here the drawn a circuit, the original circuit, and the terminals. Here, see, observe this one. This is drawn. This circuit is original circuit, and terminals are A and B. I will take the terminals whatever X, Y, or A and B. This original circuit is equivalent circuit is done as shown in figure. Here, see this one. We are seeing current source and equivalent resistance and two terminals. So here this current is called Norton's current, and the resistance is called here Norton's resistance. This current source and Norton's resistance both are in parallel. So when we derive Norton's theorem, so by simplifying the circuit, we can redraw the circuit in this way. Norton's current with resistance. This resistance is Norton's resistance is in parallel with the Norton's current. So terminals are X and Y or A and B. So this is represented in this way. Here Norton's theorem provides a method of reducing a more complex circuit. Here this original circuit is reduced complex circuit to this original circuit is reduced to simpler equivalent form. That is here this Norton's current and Norton's resistance. You understood? So now go for how to Norton's equivalent current. Here see, observe this one. Norton's equivalent current IN is denoted as IN. Here Norton's equivalent current IN is the short circuit current. IN is the short circuit current. That means IN means here ISC. ISC means short circuit current between two output terminals in a circuit. Here, IN is the short circuit current between two terminals in a circuit. So now circuit is, see here, circuit is original circuit. And the original circuit consisting of elements, they have the some elements, those are the here, see here, original circuit, Vs, supply voltage Vs, R1 is the resistance, R2 is the resistance, R3 is the resistance. Terminals A and B and load resistance RL. Here terminal A and B terminal A and B RL is connected across these two terminals. So now this original circuit by calculating by towards the, so see here, this original circuit redrawn into, so at that across the terminals AB is shorted. Now Vs supply plus or minus is same, R1, R2, R3 is same, but here step 1, the load resistance is removed and the terminals A and B shorted. A and B shorted. So when A and B shorted, the current flowing in the circuit, that is short circuit current in A and B terminals, that current is Norton's current. That current is Norton current. So here they drawn Norton's current direction IN through the earth in the loop. So they drawn in the path in the circuit. So this is the short terminals to get IN. So where we get the IN? Where they are given terminals A and B terminals. So now go for Norton's equivalent. Here they given IN. So here See one example. An example problem. See the one example problem. Determine IN for the circuit within the IN for the circuit in given area. So determine the Norton's current. Simple we say that determine the Norton's current across the load. So here the given the circuit 5 volts supply, R1 is 47 ohms and R2 is 47 ohms, R3 is 100 ohms. Load resistance is RL across the AB terminals. So here to find out the Norton's current, step 1, remove the load resistance. In step 1, remove the load resistance and short the A and B terminals. That means here AB terminals are short circuited, and so we are calculating the short circuit current ISC, that is called Norton's current. See here, observe here, A and B are shorted. Current is flowing through that is Norton's current IN is denoted. So now see here, solution. Short the terminals A and B. IN is the current through the short. So first, the total resistance seen by the voltage source is, how can we calculate the resistance, total resistance? See, observe carefully here. Now calculating of Norton's resistance Rn Rn. So first remove the load resistance RL and terminals A and B. So we seeing the circuit from the A and B terminals, and then Vs is 0. It is nothing but deactivate the voltage source. That means here the voltage source is short circuited. When the voltage source is short circuited, by seeing from the A and B terminals, we can calculate the total resistance or Norton's resistance. So here Norton's resistance Rn is equal The 47 ohms and 47 ohms both are parallel, and this parallel circuit is in series with the 100 ohms. 100 ohms. So this is the resultant Norton's resistance. Here Norton's resistance is nothing but here 47 and 47 parallel, and 100 ohms is in series with this parallel circuit of 47 ohms. So here here they given from the source seen by the voltage source. Here RT is equal to R1 plus R2 R3 by R2 plus R3. That is here from this circuit. So here 47 ohms plus 47 into 100 divided by 147 ohms, which gives the 79 ohms. The total current from the source is IT is equal to Vs by RT, that is nothing by 5 volts by 79 ohms, that is 63.3 milliamps. That is the total current from the source. So here now apply the current divide formula to find out IN. The circuit through the short means IN. Here IN is equal to R2 by R2 plus R3 IT into IT, that equal to 47 ohms by 147 ohms into 63.3 milliamps, that equal to 20.2 milliamps. This is the value for the equivalent Norton current source. Here the given Norton's current only. Given the calculated Norton's current only. So the calculated Norton's current only. So this is the value of equivalent Norton current source IN. Here next Norton's equivalent resistance. How to find the Norton's equivalent resistance? So till now what we have discussed only Norton's current, how to determine the Norton's equivalent current, how to determine the Norton's equivalent current. Here go for Norton's equivalent resistance Rn. Norton's equivalent resistance Rn is defined in the same way as RTH. That means, so in Thevenin's circuit, how we are calculating Thevenin's resistance, the same procedure is followed in here also. Same procedure is followed in Norton's theorem also. So RTH is nothing but in general we can say that Rn also. Here the Norton's equivalent resistance Rn is the total resistance appearing to output terminals in a given circuit with all sources replaced by the resistance replaced by their internal resistance. So see here in the circuit, observe this one only. Here Vs supply voltage and R1, R2, R3 across the terminals A and B, the load resistance is connected. Here load resistance is RL, supply voltage is Vs. See from this circuit, so observe this circuit, how to determine, what is the procedure to determine the Norton's resistance. How they calculated the Norton's resistance. Here by comparison of this circuit, so here Vs is short circuited, step 1, Vs is short circuited and the load resistance RL is removed. So that is removed, RL is removed from the terminals A and B. So here by seeing from the terminals A and B, that is nothing but Rn, Norton's equivalent resistance. So Rn from this circuit, by seeing from the A and B terminals, R1, R2 both are in parallel. So R1, R2 is parallel. That means here R1 into R2 by R1 plus R2. So this equivalent R1 to equivalent is in parallel. So R1, R2 by R1 plus R2. That parallel resistance is in series with the R3. Here, see here. So here, observe this one. So R1 into R Norton's equivalent is equal to R1 into R2 by R1 plus R2 plus R3. Why plus R3? It is in series with the parallel combination of R1 and R2. So now so see, for example, one example problem, Norton's equivalent resistance. Norton's equivalent resistance. Find Rn for the circuit. Rn for the circuit see example, see here this one, voltage is 5 volts, source R1 is 47 ohms, R2 is 47 ohms, R3 is 100 ohms. Because A and B, RL is not given, so we have to determine the RN from the A and B terminals. So observe this one. Observe this one. So Vs is replaced with a short 47 ohms is R1 and R2 is 47 ohms and R3 is 100 ohms. RL is removed in that place by seeing from that place terminals A and B. So calculate Rn. So here R1 and R2 both are R1 and R2 both are parallel, and this parallel will be in series with the R3. So in this way they return solution is given. So Rn is equal to R3 plus R1 by 2. That means R1 and R2 both are same. So they return R1 into R2 by R1 plus R2. So half that one. Both are R1 and R2 same. Both are, so they return R1 by 2. Or otherwise we can write R1 into R2 by R1 plus R2. Here R3 is 100 ohms and R1 into R2 by R1 plus R2 is 47 by 2. So here this is the 124 ohms. Norton's equivalent resistance is 124 ohms. Now draw the complete Norton's equivalent circuit for the original circuit that from the given problem, previous problem, that IN equal to, we got IN is equal to 20.2 milliamps, Rn is equal to 124 ohms, and terminals are A and B. So this current source in parallel with resistance, so IN is parallel with Rn. So this is the equivalent circuit from the original circuit. So here summary of Norton's theorem. In step 1, short the two terminals between which you want to find the Norton's equivalent circuit. And step 2, determine the current IN through the shorted terminals. So now step 3, determine the resistance Rn between the two open terminals with all sources replaced with their internal resistance. That means, so here ideal voltage sources shorted and ideal current sources are opened. So here Rn is equal to Rth. Why? The same procedure for determination of Rn and Rth. So now step 4, connect In and Rn in parallel to give the complete Norton's equivalent for the original circuit. See, once again you see, observe Norton's equivalent current. Here, see, once again observe this one. So here the original circuit is drawn and terminals A and B is connected with the load resistance. In step 1, so A and B terminals are shorted. So then immediately the shorted terminals get the IN current, that is IN. From this IN is calculated the current. IN is equal to from the by KVL loop. Now next one is Norton's equivalent resistance. Here Norton's equivalent resistance, see here, observe, the Norton's equivalent resistance Rn is the total resistance appearing between two output terminals in a given circuit with all sources replaced by their internal resistance. That means, see here, observe here, Vs is shorted and the load RL is removed. The whole Norton's resistance is seen by the terminals A and B. So here R1, R2 both are in parallel. This parallel combination is in series with the R3. That is the Norton's equivalent. So here this Norton's equivalent resistance in series with the here Norton's equivalent here Norton's equivalent resistance in parallel with the Norton's current. So this is the procedure for the Norton's theorem.